an alpha particle is a charged helium nucleus. Helium is much bigger than an electron. You know, it's like an enormous, great fat thing, which has got two positive charges on it. And so its range in tissue, like I said before, is not very much. It's about 40 microns. If you're, of course, it's different depending upon the energy. But most of the alpha particles we're talking about have an energy of about 5 million electron volts. And so the ranges of these things are quite short, about 40 microns. Well, what you can do in order to figure out how much ionizing effect it will have is you can divide the energy of the alpha particle, in this case 5 million electron volts, by the distance, and you get a thing called linear energy transfer, you know, and that or LET. And so what you can say is that the energy transfer within 40 microns is purely and simply the energy divided by the distance. Yeah. So in this case, 5 million electron volts divided by 40 microns. That gives you so many electron volts per micron. You can do that on an envelope. Yeah. So the number that you get, you then compare to the same number that you want to use in order to estimate the health effects of radiation, which was your original idea, was the same thing, energy per unit mass. So you take the energy per unit mass, and this depends upon the gamma ray, of course. So you get gamma rays of different energy, but most gamma rays have from normal environmental decays. If you take cesium-137, for example, which is the one everybody looks at after Chernobyl, and the one that's quite easily measured too, because it has a great big peak in the gamma spectrum at about 660 keV. That's about 0.6 MeV, incidentally. We're talking, so that's 0.6 million electron volts. Now we just remember that the alpha particles are 5 million electron volts. So this is 0.6 to 5. So just on the basis of the energy in a gamma ray is much, much less than the energy in an alpha particle. So what they did was they decided, well, we've got to do something about the fact that these alpha particles are enormously ionizing. So in other words, the energy that they put into a length of their track is enormously bigger than the energy that you get from the track from a beta particle from strontium-90 or an electron that's produced by the absorption of gamma radiation. So they decided that there were two kinds of radiation. We'll forget about neutrons for now, but basically they decided in the late 50s, early 60s, the ICRP, well, actually the Americans, the NCRP, and they're based, guess where, in Virginia, where, you know, right on top of the you-know-who. So the NCRP decided that they had to do something about this issue of plutonium, because they couldn't continue to make weapons and have places like Rocky Flats and Hanford and all that stuff producing all this shit and, you know, throwing it all over the place without being able to tell people that it was safe. So what they did was they regulated a new unit called equivalent dose. So they had the absorbed dose, and then they said equivalent dose. An equivalent dose they got from absorbed dose. They gave them different names. In those days in America, it was called the rad. That was the absorbed dose, okay, rad. I think you still use the rad, in fact. Everywhere else, people now use the sievert for some reason. Anyway, so they had the rad. The rad was the radiation absorbed dose, RAD. Okay. But obviously they couldn't use the rad for things like plutonium, because plutonium was much more hairy. It was much nastier, and it produced a lot more ions per decay. So they just plucked a number out of a hat. They said 20. What do you think, George? Oh, yeah, seems like a reasonable amount, 20. Well, we could try 10. No, 20 is a good number. And it's like my auntie's birthday and all this stuff. That's how it was done, all right, in about 1961 or 62 or something like that. And it's remained that way ever since. But actually, if you take the actual linear energy transfer, which you can do on the back of an envelope, take the MEV and divide it by distance, you can do that for anything you want. what you find is that it's a lot more. It's something like 600 the last time I did it. But anyway, you can do it yourself. So you just divide it all out and take the ratio. So this business of equivalent dose, getting the sievert from the gray or the REM, radiation equivalent man. Okay, that's your unit for the equivalent dose equivalent. You multiply by 20. So when you get when you find out that Mr. Jones has got so much plutonium in his body, you measure it in his urine, and you say, aha, he's got this amount of uranium in his body, or plutonium, or whatever. You say that his effective dose over a year, and there are all sorts of numbers for this. You can go to the ICRP and the NCRP. They've published conversion factors, dose conversion factors. So if you work out that Mr. Bloggins has inhaled so many becquerels of plutonium in the air for a year, you can go along and you can say, well, all right, this number of becquerels gives him an equivalent dose of so many REM on the basis of this multiplication factor. So you just take the number of becquerels, you multiply by the multiplication factor, and that gives you his equivalent dose. But it's all nonsense, of course, because this equivalent dose is nothing to do with 20. It's more like 500 or whatever, It's certainly not 20 anyway. So there's a whole baggage of dishonest nonsense associated with the International Commission on Radiological Protection, and they know it. They know it. I mean, in fact, the other thing I didn't tell you about, as I discovered, is that the basis of all this stuff, the basis of the risk factors, like so much radiation gives you so much cancer, was essentially the Hiroshima study, the lifespan study of the Hiroshima survivors, Nagasaki, mostly Hiroshima. And so they worked out the dose on the basis of some kind of like so much absorption and this and that. And they said that, and they measured the cancers and so on, and they compared the cancers to the dose, and that gives you their risk model. But it's complete nonsense, because most of the dose they got was from uranium. That's the fact of the matter. I mean, and we can prove that. I mean, in fact, somebody has a guy called can't remember, the Japanese guy. Anyway, I've written about it all over the place. What happened after that? When the bomb dropped in Hiroshima, it went bam. But only 5% of the enriched uranium, only 5% of it fissioned. So that means 95% of it didn't fission. So 95% of the 9 or 10 kilograms of U-235 that was there was immediately turned into particles. And those particles then became a condensation nuclei for the water that was sucked up from the sea, okay? And it all came down as rain, which they called the black rain. And this fell on people all over the place, miles away from the epicenter. They got the black rain. And so if you go and look at the cancer rates in these people who were miles away from the epicenter but got covered in black rain, they've got just as much, almost as much cancer in those people compared to a control, compared to an unexposed control in another town long way away, like 50 miles away. They've got the same sort of cancer almost as the people who were standing there and got the huge gamma ray flash. So quite clearly you can work out that it's the uranium particles, once again, I know you guys are all interested in uranium particles, the same thing at Hiroshima. Those particles were inhaled. They all landed in Hiroshima. People working in the reconstruction of Hiroshima, all these people who went there, including Australian servicemen, incidentally. I was an expert witness in a case for a guy called Mahoney, an Australian serviceman who had colon cancer. And I was managed to persuade the judge, the tribunal, that the colon cancer was caused by the immobilization of a particle in the guy's colon and produced an enormous dose close to the particle. And if you read, I published it somewhere. If you read their summing up of it, where they gave the guy a pension and they said he was killed by the uranium particle, they said it's quite reasonable that it's the dose at the point of interest that's the thing. In 1971 or 73 or 72, round about then, the ICRP suddenly changed it to the dose in the organ and not the dose at the point of interest. So that was a sleight of hand, okay?